Welcome everyone to the next IITE seminar. And today we have, I believe, our first repeat offender, and I'm very, very happy to welcome Vadim Karatayev again, who was presented a few years ago in the same seminar series when it was still young in the olden days. So actually, I will let him speak instead of me. So without further ado, Vadim, please, the floor is yours.
Yeah, thank you, Georgi and the organizers, and thank you everyone so much for coming again. And particularly thank you for the other speakers. I've been really enjoying catching up with talks in a lagged way via YouTube. And I'm really excited to share some of my recent work on two big questions in ecology, so resilience and synchrony. But this has also been kind of one of my first forays into big data. And so kind of a bigger theme I think that might be fun to discuss is how we generally can detect our favorite dynamics in nature. And I think many of us got into theoretical ecology to study cool dynamics like this. But I think like me, at some point, many of you might have heard ecologists and maybe even reviewers say something like, this is a really cool idea, but this concept was kind of a fad 10, 15 years ago, and it didn't really pan out very well, right? And so that kind of makes me wonder, like, how do we determine whether a process is important in nature? So usually over those 10, 15 years, one thing that we sometimes do is just plot data that we have right now. This doesn't seem to work very well unless whatever we're studying is just really, really dominant. To quote Ottar Bjornstad, the reason measles are kind of one of the poster childs of epidemics is that the interactions are just so strong that they punch through all of the environmental variation in the big cities. In rural areas, it's harder even with measles to predict some aspects of the outbreaks. Okay, and so this is kind of intuitive. Ecology is pretty multi-causal. It's rare that one process is going to be important everywhere. Another thing we sometimes do is experiments in the field. If we remove this process or try to remove it, is it going to change species abundances? Of course, we can only do this under a few conditions. Usually, at many scales, it's not really feasible, certainly not at the scales I'll be talking about today. And so there's always kind of that question left with realism with those. Sometimes something that we can do, one more thing that we can do is to do experiments with models of the system. So basically model selection. If we remove this process from some bigger model, does it reduce our ability to explain what we see in the world? And this is something that has a very long history, and in kind of I'm a more theoretical ecologist. I'm still trying to convince some more empirically minded folks that the way we discover new astrophysics is not by moving planets. And so this is very nice because we can account for lagged interactions and the joint influence of different processes. But the catch is that we need a decent model of the system dynamics. Okay, by that I mean something that captures a good chunk of the variability. So kind of as kind of one example of this, back in 2007 in ecology, one of our really good analyses of global population dynamics database, we fit one-dimensional models, and we found that one species was chaotic. A couple of weeks ago, Tanya gave a really beautiful talk where when we fit up to 6-dimensional models, we find that about 1/3 of the species are chaotic. Okay, so having some of the right ingredients in the right structure can be very important when we're asking how important is a particular phenomenon. So maybe we can talk a little bit more about how do we actually do this, go about finding the right model, because I think it kind of highlights, or in my experience, it's highlighted some pretty common gaps that we have in teaching ecology and theory at a graduate level. Okay, so of course, we always start with looking at patterns and dynamics. Then we pick some variables we think might be relevant to the species. Okay, and in particular, those are variables that vary on similar spatial and temporal scales. And here I think is one thing that we could maybe highlight a little bit better in teaching, which is that separation of time scales and spatial scales is the reason that simple models can work well in complex systems. After that, we of course need to pick some functional forms and fit models to data. And here I think one thing to kind of emphasize is that different systems will have different combinations of processes that are important. There's no one model that fits all, or even that's going to work for one species in different places necessarily. Another thing that's kind of coming up more and more, certainly with the data I've worked with here, which is you have these massive scales of data, which you have to pick the right spatial and temporal scale at which you're looking for some deterministic dynamics. So there's a little bit sometimes with some data sets, there's going to be an aspect of rinse and repeat here when we're picking a scale of data aggregation. And at least certainly, in my case, one of the big challenges I ran into is we know some aspects of environment that are important, but we don't know what aspect of the model they're actually impacting or what the shape of that function is. Okay, so the main thing I kind of want to talk about is some examples of how we might be able to account for environmental stochasticity. And so one of the things is that it can sometimes obscure dynamics that we're looking for. For example, here's a stochastic Rosenzweig-MacArthur predator-prey model. When we think about alternative stable states and stochasticity, we might think of this flickering, so this stochastic switching back and forth between two attractors. But if we look at something with more autocorrelated noise, again, that becomes less obvious, a little bit more subtle. Okay, so I think sometimes we don't just want to, when we're teaching, again, ecology and theory, we don't want to say that stochasticity is something that just has a little bit of fuzz in our bifurcations and our attractors. Sometimes it can really drive the dynamics. And so, if we don't account for this, especially for some important external environmental driver, the answer will be like, oh, the world is just noise. But at the same time, if we do account for that, environment can really help us identify processes because it's kind of pushing the system around in state space and it's helping us explore that. So today I want to kind of talk about how accounting and kind of really capitalizing on environmental stochasticity helps us, in this case, first of all, understand how common are tipping points in nature. This is going to be particularly kelp forests, and how do those tipping points move with climate? And here I'm going to be combining some more classical models with splines of the environment. And then secondly, how much do population dynamics vary over landscapes? And is that the reason we don't very often see population synchrony? And that's going to be more based on some newer equation-free approaches. So for this first question, I got to work with some really good kelp forest and ecologists and oceanographers. And we were focusing on kelp forests, which are one of the main kind of examples of alternative stable states, kelp forests in California. And for my PhD, I got to show that in this system, alternative stable states happen quite commonly. And the main mechanism that's driving them is a positive feedback in herbivore behavior. So when we have the slush kelp forest, there's a huge canopy, and periodically leaves of kelp get torn off, drift down to the bottom. And so the urchins can just sit in the rocky shelters and just eat the food that's delivered to them. So it's a very nice balance. But if we lose some of the kelp, then the urchins go hungry. They go out and start eating the plants directly. So then we have less plants, more urchin grazing, even less plants. And so the dynamical model of the system, which I think is pretty close to being right for how simple it is we're tracking the dynamics of kelp cover. And it's going to depend on some stochastic environmental conditions that affect recruitment. There's some shading going on. And then there's grazing on kelp and kelp recruits. And the functional form is a type 4 interaction, where if we have not much low resource density, then all the urchins are grazing actively. At high resource density, then per capita herbivore grazing actually goes down. And it's really controlled by this kind of B parameter. So we can tell, by fitting this model to data, we can let the data tell us how strong are the feedbacks. Are they pretty strong, like in this example? Or if B is 0, it's just a type 1 response, basically no alternative stable states. Okay, so we can let the data tell us which part of the reality we're in. And we've already used this model to explain spatial patterning in kelp forests in different regions. But when we look at California, the one thing we notice is the same site tends to transition back and forth between kelp and urchin-dominated states. Okay, now we know that we perfectly expect this in a stochastic world. We call this flickering. But it kind of sets us down this path, this idea that there's some kind of big disturbances that push the system back and forth. Okay, whether that's storms ripping out kelp forests or an epidemic wiping out the urchins. And the thing that seemed much less likely is climate change. Okay, so climate in the California current system is a little bit weird because it fluctuates on very long time scales. It goes every 5 to 10 years, it goes between warm water and cold water phases. Okay, and we know that this has a weak effect on kelp presence across different sites, but it's a very weak effect, and we don't even detect it if you just look at 1 or 2 sites. Okay, and this kind of makes sense intuitively because we have these really strong top-down and bottom-up interactions, and so, you know, of course, environment is probably not that important. But to double-check that kind of intuition, I modeled data from about 80 sites in 40 years in the Santa Barbara Channel. It's a pretty big region, and to estimate the impact of environment on that population growth rate, I first basically solve for the growth rate as it would be in a discrete logistic model. And then we fit this data, we fit that to a spline of environments, so in a generalized additive model. So there's nutrients, temperature, running mean of temperature, which tells us things about nutrient movement and circulation. And then we use the fitted values of the spline as covariates in our dynamical model. Okay, so there's an amount of kind of appendices and supporting information that things are identifiable when you do this. But the key idea is that we're only using environment as predictors in the spline. So this is what's helping us isolate the impact of environment on population growth. And then we say that population growth R is proportional to this fitted environmental condition. And then we fit the other dynamical model parameters of this dynamical model to data with 2-step ahead fits. And what do we find at a single reef? Okay, so what the model says is that if we, at a given temperature, the more urchins we have a shift in the tipping point until we reach the saddle node bifurcation, the kelp forest state disappears, and then we just have urchin barrens. Okay, everyone knows this. But now what we can do is ask at a given density of urchins, what is the effect of temperature? And here we find that at cool temperatures, the kelp forest state is really resilient, a really deep basin of attraction, but warmer temperatures move the tipping point a lot to the point where kind of some meaningless, trivial fluctuation in the environment is enough to trigger a collapse of the kelp forest. Okay, so I kind of really enjoy this and using this in more empirical talks because it's a really nice example of how math helps us understand the world. Yes, we have these really strong top-down and bottom-up processes, but they're delicately balanced. In warmer climates, tip the scales in favor of urchin barrens. So that's what happens locally. What happens regionally, if we average across the whole region and we look at what proportion of the reefs are barren, we see that that really always tends to tick up in warm water years. This is a dynamic that is well captured by our best fit dynamical model. And if you remember, that model said that when there's lots of urchin barrens, we should see a lot of actively grazing urchins. And that's exactly what we find in diver surveys. And I should point out that this is a behavioral rather than a numerical response. If we look at the average size of urchins over time, it's pretty much always flat. Now, the one thing I want to point out is that which process we find looks to be important is going to, in this system, really depends on spatial scale. So at a local scale, if we track just a few reefs, that hysteresis, the future depends on the past, is very obvious. All the reefs are either mostly barren or mostly forested. But it looks like there's no link with ocean climate. Okay, there's a very weak correlation. As we average to larger and larger scale, so we start basically zooming out in the system, now the role of climate is obvious, but the local dynamics are basically unpredictable because we're blind to the fact that there's hysteresis and this historical contingency going on locally. But because we were modeling dynamics of both scales, we can start to, for the system, kind of chart a path to how we might be able to maintain kelp forests in future climates. Okay, so if we do nothing, then projected warming is looks like it's going to turn most of the region into an urchin barren. But now we can ask how regional climate, so temperature and local ocean density, both shape resilience, the volume of that forest attraction basin. Okay, the gray dots here are data, so we have a good idea of this. And what we can do is say, okay, here's how much we think the system is going to warm, but we can go back and maintain the same level of resilience if we reduce ocean densities by about half. Okay, and this is typically what happens when we put in a marine protected area. And the other thing we can do with, now that we have satellites, is we can look at the geography of kelp forest resilience. Okay, so there's a couple of ways you can measure it, whether that's how often you're in a certain basin or how long you tend to stay there. All of these metrics say that in Southern and Baja California, flickering between alternative stable states is the rule throughout these 1 or 2 thousands of kilometers of coastline. Okay, so that's the characteristic dynamic of the system. It's not kind of an off chance that happens every now and then. Okay, and just to kind of explain this a little bit, every tiny faint blue dot here is a 30 by 30 meter pixel of a kelp forest. And basically all of them are in between 0 and 1. So they're all of them going back and forth between forest and barren states. So for this portion, this is highlighting that subtle levels of climate change can collapse ecosystems because they're moving tipping points. We detected this here, of course, because of the swings in ocean climate in California. That gives us peaks into what the future will look like. But also notably in other models with hysteresis, the location of tipping points in state space is also going to move whenever we shift, I think, basically any parameter. So that's something that's would be fun to look at more. We've shown that we can counteract this with local action like marine protected areas, but because climate is a regional phenomenon, these changes can span really massive spatial scales. So that's going to be a challenge. But also when we think about these really large spatial scales, kind of another reality we're faced with is that community composition and local environment are going to differ a lot between local communities. Okay, and that has always fascinated me because does this reality mean that population dynamics that emerge from these things are also going to vary from place to place too? Okay, this might be pretty depressing because then that means we need a new model for every location in a system, okay, which is kind of seems intractable empirically. Now, okay, so if that's the reality, that there's lots of heterogeneity across the landscape in dynamics, what we should see is that subpopulations for a given species are kind of fluctuating independently of one another, so low synchrony. Vice versa, we expect high synchrony if heterogeneity is lower, but also when environmental variation is kind of really synchronized across locations. Okay, so we call that the Moran effect. They're all being driven by the same forcing dynamic. And as a side note, you know, we kind of consider high synchrony as kind of a bad thing that destabilizes systems in many cases for a number of reasons, but partially because we end up with periods where the populations are kind of really sparse everywhere all at once. Okay, and that's bad for things like rescue effects. It's also bad for things like upper trophic level species, which, you know, if there's low synchrony, they can move around to a different portion of the system and kind of feed there. When you have high synchrony, you can't really do that. One of those species are, for example, fishermen, because we can't travel too far from ports and have that be economical. Okay, so here's kind of two possible things that we might expect to see. And in some systems, we do, in fact, see high synchrony, you know, some famous examples with predator-prey dynamics. And a little bit more generally, with a lot of our classical theory says that synchrony in populations should be about as high as synchrony in their environmental drivers. Okay, this is based on linearizing the dynamics. You can add a little bit more details, but it still should be on a roughly similar scale. What we find in data is that this is actually doesn't happen very often. Typically, synchrony in populations is lower than synchrony in an environment. Okay, so what this is kind of signaling is that most landscapes have some kind of resilience features built in that prevent synchrony and large-scale population declines. Okay, and so the big question is, what are these features and will they work in the future with climate change? So this is something I've been tackling for my postdoc, working with my really great mentors, Steve Munch and Dan Ruman, as well as with Tanya Rogers. And we started just kind of really broadly thinking about what are broad features that can prevent synchrony. Okay, so we're thinking about a model structure where abundance next year in a location is a function of density dependence, a function of response to the environment that those species are experiencing, and then some process error, which I won't mention after now. Okay, so if we have, for example, a system with two patches, one thing that could happen is the density dependence differs across locations. So if we have a shared environmental perturbation that reduces the population size, then we might see a response diversity between these populations. Population without allele effects is going to recover faster. Another thing that can happen is responses to environment might differ among locations, basically creating sort of like resistance diversity. Okay, so here, when we have a big heat wave pulse, one of the populations that has access to a thermal refugia, that blue one, is going to decline less than the population without access to thermal refugia. And the other thing that can happen is maybe responses to environment are identical everywhere, but populations inhabit locations with different average temperatures. Okay, so now when we have a plus 5 degrees Celsius shared heat wave anomaly in both places, absolute temperatures differ between locations. So we might only see thermal thresholds being exceeded at the southern edge of the population range. The northern latitudes are fine. Okay, so those are kind of three broad things that could happen at a very broad level. But how on earth do we kind of find what these dynamics are and how they vary across locations? How do we find the right model of landscape dynamics? And so I'm going to be using empirical dynamic models, which here's some classical and more recent references for this. Also, Tanya Rogers gave a really nice talk in the seminar a couple of weeks ago on this. And one thing that EDMs allow us to do is by using time delay embedding, we can sort of implicitly account for a lot of community dynamics. Okay, so to give you a little bit of intuition, if we have just density on the predators, but not their prey that they're interacting with, we can implicitly account for prey density using lags of predator density. So predator abundance last year, we can keep doing this. So predator abundance next year is a function of abundance now, a year ago, and 2 years ago. And continuing this on, we can approximate predator dynamics with just lags of predator density. And we can also account for spatial heterogeneity dynamics using a hierarchical formulation of these models. And we're using Gaussian processes to account for nonlinear responses to actually both environment and density. So the data we're using is going to be 36 species from the Northeast Pacific and the Northwest Atlantic. We have spatially explicit time series here, so 30 to 35 years per species, and also at 8 to 15 locations. We're spanning very large areas, so there's lots of potential for habitats and community composition to vary over space. We're pairing them with things we think might be important in the new environment, so ocean climate, summer and winter temperature, and zooplankton. And there's a much bigger temperature gradient in the Atlantic Ocean and the Northwest Atlantic. And just like in many other systems, we see the same pattern that synchrony in species is much less than synchrony in the environment. Okay, so that's what we want to explain. And so as we fed these empirical dynamic models, we see that they do a pretty good job of capturing, so the models are in blue, they do a pretty good job of capturing population dynamics and also how they vary across locations. Okay, so there's kind of lots of these plots. The idea is that they work decently. But more interesting, what we can do now is fit empirical dynamic models of different levels of complexity. Okay, and we can ask, what is the key mechanism that prevents synchrony? Okay, so that's the structure of our full model. And one thing we can look at is how important is each mechanism to explaining dynamics? Okay, how much does the R squared of a model with the mechanism increase compared to a model that doesn't have any of these mechanisms? Okay, so if we just have heterogeneity and density dependence, that doesn't seem to do much out in the Northeast Pacific. Environmental gradients also not as important. What looks really important to include in models is a heterogeneous response to environment. Okay, and then having all three improves things a little bit more. On the Atlantic side, what we see is that what's really important to include is the fact that we have gradients in the mean environment across locations. Okay, and then the heterogeneity in response to environment seems less important. The other thing we can do is ask, when we include each mechanism, how much does it reduce synchrony in our fitted model? Okay, and again, in the Northeast Pacific, we see that heterogeneous response to environment is the one that consistently reduces synchrony in all this modeled species. And in the Northwest Atlantic, again, the thing that's very important is gradients in the mean environment. Really, they should have started out with this, but these are bar plots across, box plots across all our 36 species. So each dot here is a species. And one impact of climate change that we're kind of concerned about, especially on the East Coast here, is that climate change is flattening environmental gradients, for example, as northern latitudes warm faster. And here what we find is that the bigger the gradient in the drivers that are affecting a given species, the more that species, the synchrony for that species increases when that gradient is lost or when we remove it from the model. Okay, so every dot here again is a species. So the populations in the Atlantic that tended to have lower synchrony historically might be at greater risk to this aspect of climate change. And the last thing that I kind of, the main thing I really want to emphasize is the degree to which dynamics differ across locations. Okay, so if we fit just homogeneous models, no environment, nothing, we get an average R-squared of 0.24. So this is the distribution across species. If we allow for environmental influences, then the R-squared increases to 0.37, so substantially. But we also get a really big increase in R-squared when we allow for heterogeneity in, again, density dependence and in responses to environment. Okay, so this is something that looks like it's a process that could be very ubiquitous in nature. Okay, so putting that all together, population dynamics can vary quite a lot across landscapes. It looks like they're the main reason that synchrony is often low. But which of those mechanisms is important can depend on the system. In the Northwest Atlantic, it's mostly gradients in the environment. In the Pacific, it's mostly heterogeneous responses to environment. In landscapes, then, as we just saw, modeling heterogeneity and dynamics can be as important as accounting for environment. But we can do this pretty readily with hierarchical EDMs. And the R package to this is GPEDM, which is something that Tanya has been building and maintaining. And more broadly, I think what's kind of exciting is that EDMs can accelerate and formalize part of our path to model fitting. Importantly, we can constrain the functional forms in EDMs and basically let the data tell us the parts of the system dynamics that we don't know. And then kind of what's really interesting, what's really exciting for me is to start thinking about scaling this to network dynamics. And so under what conditions can we use multi-species EDMs to resolve species interactions and how they vary over time? Okay, and for students that are savvy in dynamics and statistics, I'm very excited to be starting a quantitative resilience lab at the University of Maryland. And so I'll be kind of looking for postdocs in the next 2 years for partly projects like this, where we're combining theory and data to ask questions about resilience. For instance, how do variable food web interactions affect stability? How do integral projection models help us resolve size structure feedbacks? But also kind of more, I think, a little bit more excitingly, for a complex of theoretical questions, working on understanding hysteresis and regime shifts. How do those manifest in multi-layer networks with different kinds of species interactions, and when species interactions are dynamic over time? So I'd like to thank you all so much for listening. I'd love to answer some questions, and I have a very long list of colleagues and mentors and friends that I'm indebted to. Thank you.
Thank you so much, Vadim. So as usual, if you have questions, please raise your hand in the participant list and I will call on you. Any questions? While people are thinking, I can ask a question. which is that you've relied very heavily on R-squares as measures of model fit quality, which is fine, but we all know the limitations, that it can only improve with adding more parameters. So are there other measures of model fit, like WAIC and similar things that
yeah, of course. So under the hood, of course, this is all based on AIC. For Kelp Forest, it was BIC. But yeah, so this is kind of a very broad question. I'm always curious if other people have better ideas. So on the one hand, yeah, there's lots of problems with R squared. On the other hand, when you show someone an R squared in a talk, everyone knows what that is intuitively.
That is very true. And not to pick on the R square, it's more that I guess just seeing your models like this very superficially, it's difficult to get an intuition about how many more parameters you're adding, for example, when you're showing those shifting distributions.
Yes, yeah, and counting parameters is a little bit is a number of papers reading when we're working with Gaussian processes and those kind of very flexible forms. Yeah, with the case of the kelp forest, yeah, we're fitting those splines, but then we have seven models in the dynamical, 7 parameters in the dynamical model. So it's really not many that capture a lot.
Okay.
But yeah, if someone has, I'd love for someone to tell me a better metric to as a go-to for talks.
Yeah. In the meantime, anybody has any questions?
Wasn't that out of sample R squared, Vadim? So it's not monotonic in the number of degrees of freedom, right?
Right. Yeah, that's leave one out of sample R squared.
Oh,
correct.
thank you. Okay.
Yeah. Yeah. No, the in sample is always like 1, but that's not what we want.
Yes. Any more questions? Yes, Steve, please go ahead.
Okay, I'll give you a bit of trouble, Vadim. How generalizable do you think these approaches are? So I could argue, if I wanted to be troublesome, that kelp forests are an underwater version of measles. That is, that you have a very small number of well-identified strong interactions.
Yeah.
Okay, and so doing a literature search of my brain, which is not very good, the examples were what I think of as good examples of the play with a model approach are usually ones with a few strongly interacting species, like that one. And for the second half of your talk, to what extent does it rely on there being very long time series? What could you do with 20 years of data, for example, only 20 years of data?
Yeah, so the second question is easier. Yeah, you rely a lot on long time series. We did pretty well with 25 to 30. The fact that we have time series from many locations at once kind of helps because of the dynamics aren't different, then you kind of get some spatial replication going on. But yeah, this kind of stuff is limited to systems where you have longer time series, unless you kind of go in knowing a lot of the dynamics a priori, and you can constrain to where you're only fitting a few parts of the EDM. So then the model fitting question is, I think it's kind of one of the biggest questions in science, really, right? So like, how do we tackle these kind of complex systems? I think I don't know. I think for me, and I plan to try some of this with multi-species empirical dynamic models, but I think in my mind, a lot of the path there forward is doing more theory to start to try and understand how to networks behave, when do they behave differently from pairs of strongly interacting species? And so I found that, depending on what kinds of feedbacks you're looking at, with alternative stable states, for example, a big system like a coral reef can sometimes behave exactly like the kelp forest state. So everyone is kind of very closely, every species is really closely tied to each other. And in some other kinds of feedbacks processes that you're looking at that might be going on in nature, it's actually very complicated, and every species is kind of weakly interacting with everything. And so I think, in short, for a number of systems, it'll still work, especially those where species tend to be kind of functionally similar. And probably at certain scales, it will also work, even in some of the more diverse systems, right? If I try to predict a lot of the invertebrate species in a kelp forest, I would fail miserably because there's hundreds of them. But I think the upshot is, I feel like there's still a lot of systems and a lot of data that we're getting where there's like these low-hanging fruit where we can learn a lot about the system, even just with simple models and focusing on the few strongly interacting pieces.
Okay. This is not another question, but about, I don't know, 8 years ago, we had a paper on trying to identify environmental drivers from time series data. And our answer was about the same as what you said, that if you had about 25 or 30 years of data, then you could start to tease things out and and actually get a handle on what was driving the dynamics. And if you had shorter time series, it was pretty much hopeless.
Yeah. I think, well, it's a little bit of a cheesy answer, but I think one of the most important advances in ecology is that time series that started in the 1990s are now 30 years long.
Well said, and thank you.
And importantly, more accessible.
Yes,
Sometimes.
very important. Are there any other questions? No questions? It seems there are no more questions. So in that case, thank you so much again, Vadim, for coming and giving this very interesting talk. And for everybody else, we shall see you the next time, which I'm not sure when it is, but our calendar knows, and we shall send out an invite in time. So see you then.
The next time is in January 23, and it will ship to your podcast.
Okay, so Tulja is going to be talking in January. So in that case, have a great rest of your day and a great rest of your year, and we shall see you in January.
Happy holidays, everyone.
Bye, everyone. Take care.
Bye.